So the example that I am going to take is a completely artificial contrived example. I am just going to write node names over here. They do not correspond to any, they need not be adders or multipliers, they can be any arbitrary computational units. I am just going to call them A, B, C, D, etc. So this is some arbitrary data flow graph. Okay, like I said, the actual computations being performed by A, B, C, D, etc. I do not care about. All that I care is they take certain inputs if necessary. I mean, so A for example does not take inputs, but it does generate outputs. All the others B, C, etc. take some inputs and generate outputs. The assumption I am going to make further over here is that dA is equal to dB, etc. All of them have the same delay value equal to 1 time unit. Again, like I said, that time unit is irrelevant. It could be 1 clock cycle, it could be 1 nanosecond, it could be any time unit, as long as I am consistent in the comparisons that I am doing across all the different implementations. Okay, so this is what I have, right? And let us say I have, as far as my hardware is concerned, I have separate hardware modules for implementing A, B, C, D, E and F. Okay, so there are 6 pieces of hardware, right, that are capable of implementing this. Each of those hardware units essentially takes this 1 time unit to execute its particular function. Okay, and as a result, and you can even think of these as combinational gates, AND gates, OR gates if you want to. Okay. Therefore, if I now ask the question, if I consider this entire system as 1 unit, what is the critical path and therefore the best iteration period that I can get for this implementation, right? What would you say is the critical path through this circuit? How many time units? Shout one number. What is the critical path? It is the longest path through this circuit. Okay. So in this particular case, if I start looking for the critical path, what I will find is that there is one path over here which starts from A, goes to E, goes up to C, comes to F and then to D. And this path essentially has a length which is 5 time units. So in other words, what it is saying is, once I have triggered the execution of A, right, in this case I do not have any inputs going into A, but if I did have inputs and something happens, A executes, it generates outputs, those then go, those outputs are copied to B and E, B and E then execute because they are after all working on separate pieces of hardware, right. They generate their outputs that are then in turn consumed by C, and then once C has also finished is only when I can run F. So even though the output of E might be ready at time 2, right, F cannot directly execute then because it is still waiting for something from C, right. So this is exactly the notion of critical path, right, and ultimately it determines what is the minimum clock period or iteration period that I can use for this. Just for reference, what should the iteration period bound of this circuit be? What is the iteration period bound? Going back to what we discussed last week, the iteration period bound is the minimum achievable theoretical iteration period. I mean, even in theory, assuming infinite hardware, what is the minimum iteration period that can be achieved for this circuit? 0, right? There are no loops over here, so there are no feedback loops. This is an example of something that is completely feed forward. If I have sufficient amount of hardware, right, it is just like the case of the FIR filter. I could take all my x of n values, my inputs, and feed them into infinite number of copies of A. Those outputs will then feed into infinite copies of, n copies of B and C, B and E, then C, F, D, right, in that sequence, which means that within 5 time units I could basically finish n iterations. As n tends to infinity, the iteration period could be brought down as low as I wanted if I had infinite hardware. So the theoretical bound over here is 0, but the practical bound is going to be obviously very different because I have only one piece of hardware each for A, B, C, D, E and F. So one way of looking at that is A by itself imposes a loop, right. I can think of it basically as having a self loop over here with one delay element saying that only after A has finished once, it can then start again on the next iteration. And if I had this kind of a self loop on each and every one of my operations, or my hardware units. Now what would the iteration period bound be? I have loops. There is a loop around A. The loop delay through it, the total execution delay is dA equal to 1 time unit. The number of tokens on it is 1. Therefore, the iteration bound as far as the loop around A is concerned is 1. Okay. So, in other words, for the green version, the iteration period bound is going to be max of, in other words, 1 time unit. Okay. So, as long as I have only one piece of hardware for each of these units of execution, that is A, B, C, D, E and F, I am limited to at best having 1 time unit as my minimum iteration period. Okay. All right. So, right now what we have seen is the critical path of this circuit as it stands, which is marked in magenta over here, is 5 time units. The question I am asking is, if I want to bring it down, I mean in theory I can bring it down all the way to 0 if I have infinite hardware. Even if I do not have infinite hardware, I have only these resources, my iteration period bound is still 1, it is not 5. Okay. So, 5 is clearly much more than what I should be looking at. Okay. If I wanted to bring my iteration period down to 3, the clock period that I can use for this, how would I go about doing it? Okay. So, let us just redraw this very quickly so that it becomes a bit clearer. Okay. So, the first thing is that the critical path, if I write down the nodes on the critical path, what are they? It is going to be A, E, C, F and D, right, for a total of 5 time units. If I want to bring down the length of the critical path, the number of nodes or the total execution time delay on that critical path to 3 or less, how can I do this? I need to break this path. I cannot have A, E, C, F, D as one long path through the circuit. I can break it. Where should I break it? In other words, in this particular case, there are, I mean, if I break it between A and E, for example, will it help? No, I mean that by itself will not bring down the critical path below 3 or to 3, right. In other words, if I was to go and put a break over here, then I would get 1 and 4, which is not really solving my problem. Okay. Instead, if I put a break here, I would get 2 over here and 3 on this side, which is one possibility. If I break it here, I would get 3 on this side and 2 on this side, which is also okay. But if I break it here, I would get 4 on this side and 1 on this side, which is again not solving my problem. Okay. Right. So, one of these two is possibly what I am going to be looking at, right. Either I break the critical path between E and C or between C and F.